Have you ever wondered why a paperclip springs back if you bend it a little, but stays bent if you push it too far? That specific moment is the difference between a safe structure and a catastrophe. Today, we're breaking down the physics behind it. If you were a mechanical engineering student or just curious about how materials work, you have to master two fundamental concepts: stress and strain. Most people use these words interchangeably in daily life, like, "I'm under so much stress," or "this is putting a strain on our relationship." But in engineering, they mean two very different but mathematically precise things. By the end of this video, you'll understand the stress-strain curve, the difference between elastic region and plastic deformation, and exactly when a material decides to give up and break. Part 1. Defining the players. Let's keep this visually simple. Imagine a rectangular metal bar. When we pull on it, we are applying a load or force. Now, stress is internal. It is the internal resistance of the material to that applied force. Mathematically, it's force divided by the cross-sectional area. Think of it as pressure inside the material trying to hold it together. Strain, on the other hand, is geometric. It is the measure of how much that material deforms. It's the change in length divided by the original length. Basically, it's a percentage of stretch. Here is the fastest way to remember the difference. Stress is what the material feels inside, the pressure. Strain is what you see on the outside, the stretch or deformation. You can have stress without visible strain, but you usually need stress to cause strain. So in summary, stress is the load intensity. Strain is the deformation intensity. Part 2. The stress-strain curve. Now, let's plot these against each other to create the famous stress-strain curve. This is the holy grail of material science. At the beginning, as we pull the bar, stress and strain rise together in a straight line. This is called the elastic region. In this zone, the material is acting like a spring. If you let go of the force, the bar snaps back to its original shape perfectly. The slope of this line is known as Young's modulus, which tells us how stiff the material is. Steeper line, stiffer material. But what happens if we keep pulling? We hit the yield point. This is the point of no return. Once you pass this point, you have left the elastic region and entered the zone of plastic deformation. Think of elastic deformation like a rubber band. You stretch it and it returns to normal. Plastic deformation is like chewing gum. Once you stretch it out, it stays stretched forever. In engineering, once you pass the yield point, your material is permanently changed. It will never go back to its original size. Part 3. The paperclip example. Let's apply this to our paperclip to see engineering stress in action. When I bend this paperclip just a tiny bit, I am staying in the elastic region. The atoms inside the metal are stretching apart, but they haven't slipped past each other yet. When I let go, it springs back. But here, I pushed it too far. I exceeded the yield point. The stress was too high, causing permanent plastic deformation. The atoms have physically rearranged themselves. Now, look at the graph again. If I keep bending this back and forth, or pull it with extreme force, the material hardens. Stress builds up to the ultimate tensile strength, the maximum stress it can handle, and eventually, it breaks. That is the fracture point. Every material has a limit. On the stress-strain curve, the highest peak is the ultimate strength. But the end of the line? That's fracture. Whether it's a bridge, a beam, or a paperclip, if you push strain too far past the plastic zone, failure is guaranteed. So, next time you look at a bridge or a building, remember that engineers have calculated exactly how much stress those beams can take to ensure they stay safely in the elastic region, far away from that dangerous yield point. Just remember these three key points. Stress is the force over an area. Strain is the deformation. The curve tells the story of the material's life from elastic stretch to plastic failure. If you found this helpful, please hit that like button. It really helps the channel. Thank you so much for watching. If you liked the video, please consider subscribing, liking, and sharing this video with others who are interested in simple engineering.